theorem. First of all, we will see the Bernoulli's theorem. It states that the total energy in a flow field at any point along the streamline remains constant. It is nothing but an energy balance equation. The assumptions which are made in the Bernoulli's theorem are steady and incompressible flow, ideal fluid flow, flow is irrotational, and the flow is along streamline, where the ideal fluid flow means the flow is inviscid. Here we will see the flow through a pipe where we have taken two sections, section 1 and section 2. The discharge passing through the pipe is Q, while the pressure and the velocity at point 1 and 2 are P1 and P2, while the datum heads are Z1 and Z2. By applying the continuity equation between point 1 and point 2, we can say that Q is equal to A1 V1 is equal to A2 V2, where the densities are constant at section 1 and 2 as the flow is incompressible. So by applying Bernoulli's theorem, we will get the equation P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. The losses between section 1 and 2 are 0 for ideal flow. Now we will see the application of Bernoulli's theorem. So there are major two types of applications of Bernoulli's theorem. One is for flow measurement, so that we are going to see in this unit itself. The second one is other hydraulic system applications. The first one, flow measurement. So for measuring the internal and external flow, where we can say the internal flow means the flow through a pipes or ducts, and the external flow means the flow through the canals or rivers, or we can say open channel flow. So for that purpose we can easily apply the Bernoulli's theorem, and we can say that Bernoulli's theorem plays a very good role. So the first one is Venturimeter. It is used to measure a flow through a pipe, where the U-tube differential manometer is used to measure a loss of head across the convergent section of Venturimeter, and this loss of head is used to measure a theoretical discharge. Second one is Orifice Meter. It is again a same type of device as Venturi Meter, which works on pressure difference, and this pressure difference is used for the measurement of discharge. The third one is a pitot tube. So it can be used for the measurement of flow through a pipes, as well as measurement of flow through a rivers or the open channel flow. So means it can be used for the flow measurement of internal as well as external flow. The fourth one is notches and wears. So notches and wears are same in shape, only the difference is that the size of notch is less than the size of wears. These are the sections made at the discharge points on the discharge walls, so that the discharge can be measured. So notches are generally used for measuring a leakage through the dam walls, while the weirs are used to measure a discharge through the dams in case of flooding or discharge in a rivers whenever it is required for the irrigation as well as for the purpose of drinking. Other applications include the pipe fittings and pipelines. So where the pipe fittings are generally the walls, bends, then the T sections, the branches that are made in a piping system, and many more applications are there. The pump system and the turbine systems also uses the Bernoulli's theorem, where pumps use the Bernoulli's theorem to measure a head achieved by a pump or head required to be achieved by a pump so that the selection of pump can be made properly. Turbines. So turbine selection again depends on the amount of head available in a dam or reservoir, and based on this how much of energy that the turbine can develop. So this is how the Bernoulli's equation can be used. So again, the design of dam walls as well as the discharge to the dams requires the application of Bernoulli's theorem. So this is all for application of Bernoulli's theorem. Now we will move towards the Venturimeter. It's a very simple device. It consists of three sections. One is convergent cone, second one is throat, third one is divergent cone. It is fitted in a pipe where the convergent cone is facing the flow while the flow leaves the venturimeter through the divergent section. The convergent cone angle is between 15 to 21 degree. So it is for achieving the pressure difference or for creating a pressure difference, and this pressure difference can be measured by U-tube differential manometer. The U-tube differential manometer's one end is connected just before the convergent section and the other end is connected on the throat section. The differential U-tube manometer carries the manometric fluid and will get the manometric head difference delta H. Followed by this convergent cone, we have a throat section. It is a uniform diameter pipe which works as pressure stabilizer for accurate pressure measurement across the convergent cone. The divergent cone angle is in between 5 to 7 degrees, so it avoids the flow as well as the boundary layer separation and reduces the loss of energy. So we'll see the how the discharge can be measured by application of Bernoulli's theorem. So here take point 1 and 2 where the ends of U-tube differential manometers are attached. So P1, V1, Z1 are the pressure, velocity and datum head at just inlet to convergent cone, while P2, V2, Z2 are the pressure, velocity and datum head at the throat section. Here the delta H is a manometric head difference between point 1 and point 2. Let H is a piezometric head difference. We know that the piezometric head is nothing but the sum of pressure head and the datum head. So based on this, the piezometric head at point 1 is P1 upon rho g plus Z1, while the piezometric head at point 2 is P2 upon rho g plus Z2, and the difference between the piezometric head at point 1 and point 2 is nothing but the pressure head difference between the 2 points. Let rho m and rho w are the densities of manometric and working fluid. So based on this, the relationship between manometric head difference and the piezometric head difference can be very easily obtained, and this is H is equal to rho m upon rho w minus 1 into delta H. By applying the Bernoulli's theorem between the point 1 and point 2, assuming the same assumptions that we made while deriving the Bernoulli's theorem, it is P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. This is equation number 3. Rearranging the equation 3, in order to get the piezometric head difference. So it is P1 upon rho g plus Z1 minus taking the P2 by rho g and Z2 on the left hand side. So minus it is P2 upon rho g plus Z2 is equal to V2 square upon 2g, taking V1 square upon 2g on the right hand side, that is minus V1 square upon twice g. Now we will apply the continuity equation between point 1 and point 2. So the discharge at point 1 must be equal to the discharge at the point 2, and based on this, Q theoretical is equal to rho 1 is equal to A1 V1 is equal to A2 V2. Rearrange the equation 5. V1 is equal to A2 upon A1 into V2. Now putting the V1 in the equation number 4, so we will get P1 upon rho g plus Z1 minus P2 upon rho g plus Z2 is equal to V2 square upon 2g minus V1 square upon 2g is equal to V2 square upon 2g minus 1 upon twice of g multiplied by in bracket A2 upon A1 V2 bracket square. So simplifying this, you will get H is equal to V2 square upon twice of G in bracket 1 minus A2 square minus A1 square. Again rearrange, equating the denominators. H is equal to V2 square upon twice of G in bracket A1 square minus A2 square upon A1 square. So again rearrange equation of H to obtain value of V2. So V2 square is equal to, taking 2g on the left hand side, it is 2gh. Again taking A1 square minus A2 square upon A1 square on the left hand side, it will be A1 square upon A1 square minus A2 square. So taking the square root of equation 7, so it is square root of A1 square is A1, while the square root of 2gh is square root of 2gh. The square root of A1 square minus A2 square is square root of A1 square minus A2 square. So V2 is equal to A1 root of 2gh upon root of A1 square minus A2 square. So this is equation number 8. Now putting the V2 in the equation number 5, we will get Q theoretical is equal to A2 V2, that is equal to A2 into, putting the value of V2, A2 into A1 root of 2gh divided by root of A1 square minus A2 square. So the theoretical discharge through the pipe can be obtained as Q theoretical is equal to A1 A2 root of 2gh divided by root of A1 square minus A2 square. But in actual, the losses always occurs in a real fluid flow, hence the actual discharge is always less than the theoretical discharge. Hence we have a term called coefficient of discharge. It is the ratio of actual discharge to a theoretical discharge. CD is equal to Q actual upon Q theoretical, where Q actual can be obtained by multiplication of CD and Q theoretical. So Q actual is equal to CD into, putting the value of Q theoretical from the equation number 9, CD into A1 A2 root of 2gh divided by root of A1 square minus A2 square